Now that we have learned the probability function and the axioms that we are supposed to believe in about it, and also we have learned some simple propositions on probability which are going to be helpful to solve many types of probability questions. Here we are going to learn about some probability questions related to sample spaces with equally likely outcomes. So this is not a very practical situation as always, but usually it is natural to assume that all outcomes in the sample space are equally likely to occur. For example, when you flip a coin, you either get a head or tail, and of course you are assuming that this is a fair coin and these two sides have the same chances of 1/2. Or when you toss a fair die, you have 6 sides of this die, and obviously you are assigning equal chances to each of these integer values on the faces of the die. So this is basically a natural assumption in many cases, assuming that each outcome is fairly and equally likely to occur. Now, suppose we have a sample space S, and it is finite. We have a countable number of outcomes in that sample space. And as we have said, it is natural to assume that the probability of each outcome in the sample space is equal to each other. So here, if you take the capital N equal to 6, you are going to get the sample space of the experiment where we toss a fair die, and each probability assigned to each integer from 1 to 6 is going to be equal to each other. So this is the assumption of a fair die. But here, we are assuming that the sample space has n many outcomes, and each of which is equally likely to occur, which means the probability of each outcome is equal to each other. Now, we know that the sample space has the probability that is equal to 1. The whole sample space probability is equal to 1. And we know that the sum of disjoint events in the same sample space is going to be equal to their union. And the union of all outcomes here gives us the sample space. Therefore, using the axioms of probability, we can see that in such a case where we have a sample space where each outcome has the equal chance to occur, the probability of each outcome should be equal to 1/n. So, for example, in the die experiment, each face of the die has the probability of 1/6. Or in the coin toss experiment, a head or tail will have the probability of 1/2. So in a sample space with equally likely outcomes, if we have n outcomes, in that case, each outcome will have the probability of 1/n. So for all outcomes I, changing from 1 to n, we will assign the probability of 1/n. Now, how about the probability of other events? If you are given an event in the form of any subset of the sample space, in that case, the probability of that event will be calculated as the number of outcomes we observe in the event E in that subset divided by the total number of outcomes in the sample space. Or in other words, the number of elements in subset E in event E divided by the number of outcomes in the whole sample space. Or in other words, we can say the cardinality of the event E is divided by the cardinality of the sample space. So basically, if we want to summarize the learnings here, if we assume that the outcomes of an experiment are all equally likely to occur, so equally likely means with equal probabilities, with equal chances, then the probability of any event E equals to the proportion of outcomes in the sample space that are contained in E. So the probability of an event would be the proportional to the number of outcomes in that event subset. So the question here is basically a practical application of what we have learned in the previous pages. Here we have a random experiment where we roll 2 fair dice. We know that if you toss or roll 2 fair dice, the number of possible outcomes in that sample space would be 36, which is obtained by 6 by 6 by the basic principle of counting. Now, we have a sample space with 36 outcomes, and we can assume that because the dice are fair here, sample space has outcomes which are equally likely to occur. So the question asks first, what is the probability that the sum of the upturned faces will equal to 6? Now, if we answer that question first, in order to answer that, first we need to write down the whole sample space as a list, and you see we have 36 possible outcomes here as the outcome of two fair dice. Now, in this sample space, which outcomes correspond to the event of having the sum of two outcomes equals to 6? So I have just indicated these outcomes with a star sign on the corner of them. So if you get a 5-1 or 4-2 or 3-3 or 2-4 or 1-5, you can simply say the sum is equal to 6. Now, this subset E in the sample space corresponds to the event of the sum of two dice to be equal to 6. And how many outcomes do we have here? We have 5. Therefore, assuming that all these 36 outcomes are equally likely to occur, the probability of the sum of the upturned faces to be equal to 6, or the probability of event E, or the probability of this subset will be equal to 5/36. Now, please do not forget, we can only calculate this probability because we have assumed that all 36 outcomes in the sample space are equally likely to occur. They have equal chances. There are some sample spaces where the outcomes do not have equal chances to occur as well. So in these kind of sample spaces, we cannot use this analogy. Now let's go back to our question and let's answer question second part B. What is the probability that the minimum of the upturned faces will equal to 2? Now, when you toss two fair die, you will see two numbers, and one of them is going to be less than the other one, okay, or at least equal to the other one. So that value is called the minimum of the upturned faces, okay? So when you toss two fair die, the minimum of the values that you see in front of you, minimum of the two values, is called the minimum of the upturned faces. And the question is asking, what is the probability that the minimum of the upturned faces will be equal to 2? Now, how do we solve this question? In a similar fashion that we have solved part A. Now, in part B, as you can see, again, we write down our sample space, the whole sample space, and indicate which outcomes in the sample space correspond to the event of the minimum of the upturned faces to be equal to 2. Now, you see, if you get a 6-2, the minimum of 6 and 2 will be 2, and you can say event F has occurred. If you get a 5-2, 4-2, 3-2, or 2-2, in these outcomes, the minimum of these two faces are going to be always 2. But not just these outcomes. If you get a 2-3, 2-4, 2-5, or 2-6 as well, the minimum of the two faces is going to be assumed as 2. Now, if you check other outcomes, in the other outcomes, you do not have that situation. Therefore, if we represent the minimum of the upturned faces to be equal to 2 as an event F, then F is going to be a subset of the sample space containing these 9 outcomes. And again, assuming that each outcome is equally likely to occur in the sample space, the probability of event F, subset F, would be the cardinality of F, which is 9, divided by the cardinality of the sample space, which is 36, and that would be 0.25 in this case. And if we go back to read our third part of the question, what is the probability that the product of the upturned faces will equal to 12? So here it says product. Product means multiplication, okay? So what is the probability that the multiplication of the upturned faces will be equal to 12? Now, again, in part C as well, we write down our sample space with 36 outcomes, and we check which outcomes correspond to a product when you multiply the two values with each other. is equal to 12. And if you get a 6-2 or 4-3 or 3-4 or 2-6, you can say the product of the upturned faces is equal to 12. And we represent that event as event G, then the event G will be represented by this subset of the sample space, which has 4 equally likely outcomes among 36 equally likely outcomes. So the probability of event G will be equal to cardinality of divided cardinality of S, which is 4 over 36, and in summary, 1 over 9. So this example was just a practical example where we have solved a few probability questions on a random experiment which has a sample space with equally likely outcomes. And this next question again is going to use the same understanding. Again, we are going to define a random experiment in this question, and in that random experiment, we will have a sample space where each outcome is equally likely to occur. So we can answer simple probability questions. Okay, so the question is as follows. If 3 balls are randomly drawn from a bowl containing 6 white and 5 black balls, what is the probability that one of the balls is white and the other 2 is black? So here's the case. We have a ball. In that ball, there were 11 balls, and 6 of them are white and 5 of them are black. Now, we are randomly selecting 3 balls from that ball, and the question is asking the probability that we get a single white and 2 black balls among this. So what is the probability of selecting 1 white and 2 black balls in that random selection process? First of all, if we assume this as a random experiment, what is this experiment? Randomly drawing 3 balls from a ball that contains 11 balls, right? So we are selecting 3 balls out of 11. And in how many different ways we can select these 3 balls from these 11 balls? So you see, we are going to use the number of combination formula here. So we have learned in combinatorial analysis that we can create 11 choose 3 many subsets from a set of 11 elements if we want to create 3 element subsets, right? So 11 choose 3 is the number of 3 element combinations of this element of this set we have where we have 11 elements. So basically the sample space of this random experiment will have this many elements. Okay, so we have learned this combinatorial analysis concept, and the things that we have learned there would be helpful to us to count the number of elements in the sample space and the elements in certain events, right? So basically here 11 choose 3 is the number of outcomes that we may observe in the random experiment. And that is equal to 165 if you do the calculation. Now, let's focus on the event of interest. The event of interest is selecting 1 white and 2 black balls. Now, in the event of interest E, we need to select 1 white ball out of 6 white balls in the bowl, and other 2 should be black out of 5 black balls. Now, in how many different ways we can select these balls in this event? So we need to choose 1 ball out of 6 whites times we need to choose 2 black balls out of 5. Right? So we are using the number of combination formulation and also the basic principle of counting, and we can count the number of ways in which we can select 1 white and 2 black ball when we select randomly 3 balls out of the zone, and that would be equal to 60. So basically, the probability of event E is going to be equal to the number of outcomes that we observe in E and the number of outcomes that we observe in the sample space. So in the numerator, we write 6 choose 1 and 5 choose 2 multiplied. In the denominator, we write 11 choose 3. And after some calculations, you would get 60 over 165, or in short, 4 over 11 as a result of this question. So you see, in this question, we have used the understanding of the sample spaces with equally likely outcomes, assuming that when you select randomly 3 balls, any kind of outcome would have the same chances. And we have also used the concepts that we have learned in the combinatorial analysis chapter to count the number of outcomes in the sample space and the number of outcomes in the event of interest. Now we are going to solve another question. Again, it is going to be an example question on the sample spaces with equally likely outcomes. It says there are 5 hotels in a certain town. If 3 guests randomly check into hotels in a day, what is the probability that they each check into a different hotel? Now, imagine we have 5 hotels, and in the beginning of the day, 3 guests are going to arrive to that town. Now, each guest is randomly selecting a hotel. And at this point, please do not focus on the question. Just focus on the random experiment procedure. We are going to answer the probability of the event of interest later. So at this point, it says 3 guests are randomly check into the hotels. Some of these guests can check into the same hotel, or maybe all of them can check into a different hotel. So at this point, we need to count in how many different ways this experiment can end up with. So how many outcomes we may have. Now, each guest, the first guest can check into any of the 5 hotels. And if we give the same chance to the second guest, the second guest can also check in any of these 5 hotels. And the third guest can check in any of these 5 hotels, right? Therefore, assuming that this is a random experiment, this random experiment can end up with 5 to the power 3, 125 equally likely outcomes. So by the generalized principle of counting, we are assuming that each guest's check-in process is an experiment, and we have 3 experiments, and when we combine these 3 experiments by the generalized principle of counting, we would have 125 equally likely outcomes. So the question here is this: what is the probability that they each check into a different hotel? So what is the probability that all these guests are checked in a different hotel? Now what we are going to do is, we are going to represent this event as event E, and we are going to count the number of ways, different ways, these guests can check into different hotels. Now, let's just say the first guest arriving to the city can check into any of the 5 hotels, right? But once the check-in process is complete for the first guest, if we would like them to be in different hotels, then the second guest can only check into the remaining 4 hotels. So first experiment has 5 outcomes. However, given that the first experiment is over, then if we want the event of interest to occur, which is for all guests to check into different hotels, and the second guest will only have 4 different hotels that he or she can check in. Now, after the second check-in is complete, then for the third guest, there will be 3 remaining hotels. As a result, the number of outcomes in which all these 3 guests are checking into different hotels is equal to 5 times 4 times 3 by the generalized principle of counting. Actually, this question is using the number of subset permutations. So we are basically using the permutation analogy here. Now, in 60 different ways, we can make this guest check into different hotels. Now, the probability of interest is that the cardinality of event E, which is 60, divided by the cardinality of the sample space, which is 125. And that is, in summary, 12 over 25, which is very close to 0.5 if you are careful. So there is almost, not exactly, but almost equal chances for everybody to check in different hotel or somebody to check in the same hotel. So that probability is 12 over 25 for everybody to check in different hotels. Now, in this question, we are going to have an urn that contains 100 balls. Okay, so this question actually is very similar to the question that we have solved earlier, where we had 11 balls in the urn. This time we have 100 balls in that urn, two of which are spatial. So let's just assume there are two golden balls, okay? And the remaining 98 balls are ordinary balls. If 60 of these balls are withdrawn, one at a time, with each selection being equally likely to be any of the remaining balls at that time. So here's the question. We are selecting these 60 balls randomly, one by one, and we are always selecting from the remaining balls. The next ball is selected from the remaining balls, which means when we select a ball, we are just taking it outside and putting it aside. The next ball is going to be selected from the remaining balls in that turn. So this process is called without replacement selection. So it's a selection process or withdrawal process without replacement, because we are not replacing the previously selected balls into that urn again. So it is without replacement. Now, without replacement selection is actually very similar to selecting all these 60 balls all together at one time. So either you select one by one and put them aside, or you select if you have a very, very large hand, okay, assuming that you have a very large hand, and you can check the count of the number of balls that you have selected when in the selection process. I mean, you can select all the 60 balls at a single shot from that urn, okay? So without replacement selection, and that process would be the same. So the question here is this. You are selecting 60 balls randomly out of 100 balls. What is the probability that at least one spatial ball is in chosen 60 balls? So what is the probability that you come up at least one golden ball? Okay, so how do you calculate this question? Now, actually, in order to answer this question, you need to first calculate the probability of selecting no spatial ball. Okay, so here it says the event of selecting at least one spatial ball. Okay, what is the complement of this event? Is selecting no spatial ball. So if I find the probability of that event, then I will use the first proposition of probability to calculate the complement events probability, right? So let's calculate the probability of selecting no spatial balls. So in this experiment, you are choosing 60 balls out of 100, and this is going to be the number of outcomes that you may observe in your sample space. Now, my friends, if you intend to calculate 100 choose 60, that would be a very, very large number, unfortunately. Please do not try to do that. Instead, just denote it with this number of combinations formulation at this first place. Now, let's focus on the event of interest. At this point, we are only interested in the event of selecting no spatial balls. Please be careful. We are not answering the question. We are answering the probability of its complement at the first point. So, in how many different ways I can select no spatial balls? This means I'm going to choose 0 out of these two spatial balls and 60 out of the remaining 98 ordinary balls. So again, by the basic principle of counting, we multiply these two number of combination formulations. Now, if you expand 2 choose 0, you will simply get 1. Now, you will expand 98 choose 60 and 100 choose 60 in the numerator and in the denominator, and you will easily realize that 60 factorials will cancel out, and we have 98 factorial over 38 factorial here, and we have 100 factorial over 48 factorial here, and the remaining values can cancel out as well. For example, if you have 98 factorial here and 100 factorial here, you will get 199 in the denominator here, and the remaining values will be cancelled out. Similarly, 40 factorial and 38 factorial here, and that 40 and 39 will remain in the numerator. As a result, after these cancelling operations, you would simply get 26 over 165 as the probability of selecting no ordinary balls. Now remember, the question was asking us the probability of selecting at least one spatial ball, which is basically the complement of the event of selecting no spatial balls. Therefore, what you are going to do is, you are going to subtract that probability from 1, and the probability of selecting at least one golden ball is 139 over 165. All right, so this is just going to be the last question that we are going to solve about the sample spaces with equally likely outcomes. In a class of 25 students, there are 3 project teams of 7 members. If we randomly select 6 students from the class, what is the probability of selecting 2 students from each team? So right now, there are 21 students in a class, okay? And we have 3 project teams. Each project team has an equal number of members, 7, 7, 7. And we are randomly selecting 6 students from that class. What is the probability that we select 2 members from each project? Now, you can also ask the same question in another fashion. Assume that we have 21 balls in an urn, and 7 of them are black, 7 of them are white, and 7 of them are red. If we randomly select 6 balls from that urn, what is the probability that we will have equal number of balls from each color? So the same question can be asked in a different manner. So what you are going to do is this. First, you are going to count the number of different ways how you can select 6 students out of 21 students. So that would be 21 choose 6. And for the event of interest, you are going to count the outcomes in that subset. And in how many different ways you can select 2 students from each team. So by the generalized principle of counting, 7 choose 2 times 7 choose 2 times 7 choose 2. And after canceling out the factorial operations carefully, you would get a probability that is the ratio of 441 over 2,584. That is going to be approximately equal to 0.1707. Okay. So please take note that in all of the questions that we have solved in this video, except the experiment where we toss 2 die, we have used the learnings, the concepts we have covered in the combinatorial analysis chapter. It is therefore these combinatorial analyses are very important for us because they are going to be very useful in calculation of the probabilities. Counting is an essential process for calculating simple probabilities.